Okay, so we're going to move on to question 3. And looking at question 3, we're going to continue um, writing our given statements first. Given, we have a standard deviation of 60 psi. We have a sample of 12 specimens. That sample mean is equal to 3,450 psi. And we're going to look at the level of significance if the mean strength was 3,500. So if mu is equal to 3,500, what is your p-value? Because that's what the smallest level of significance is. It's the p-value for that given mu. So the p-value is going to be equal to 2 times 1 minus the z-statistic of the 3,450 minus 3,500 divided by our standard deviation of 60 divided by our square root of 12, or our n. And so when we crunch that down, we're actually looking at the absolute value of that. When we have a two-sided test, we use the absolute value. So we've got 2 times 1 minus the test statistic for 2.89. So even though that number came out to be a negative when you're doing a two-sided test, you are able to use the absolute value. And so that is equal to 2 times 1 minus 0.9981, and that is equal to 0.0038. So then it says if the true mean is 3,470 and alpha is 0.01, find the error and the power. So now we're going to see that the true mean is equal to 3,470, and we're going to use an alpha of 0.01. So we're looking at, again, that formula that the power is going to be equal to the z-test statistic of z alpha over 2 minus the difference between the means times the square root of n over the standard deviation minus the negative z alpha over 2 minus the difference of the means times the square root of n over sigma. And so in this case, when we have an alpha of 0.01, our z of alpha over 2 is equal to 2.58. And so I can plug in 2.58 minus negative 30, because that's the difference between the means, multiplied by the square root of 12 over 60, minus a negative 2.58 minus negative 30, multiplied by the square root of 12, divided by 60. And so remember that the difference between the two means was equal to 3,470 minus 3,500, because that was the mean that was given to us. So the difference between the two means was equal to negative 30, and we had that funky little symbol that we use for the difference between the means. So when you're looking at the formula and you see that funky little symbol, that's the difference between the means. So this crunches down to the test statistic for 4.31 minus negative 0.85. And so 4.31, again, that's off our chart. So we look at that as 100% minus 0.1977, which is equal to 0.8023. And now we're going to look at the power. And the power is equal to 1 minus beta. And so that's equal to 1 minus 0.8023, which gives us 0.1977. So we're going to flip it around a little bit. We're going to say, well, what if we want the power of that test to be 80%? What if we want to reject the null hypothesis um, with a probability of 80% if the mean was 3,470? And so what sample size do we need to get that power? Because we're at like 20% right now, 19.77. We're looking at like 20% power right now. That's not really good. So our z of beta is actually equal to z of 0.2. And that, when we look it up on the chart, is 0.84. And our z of alpha over 2 is still that 0.005 or 2.58, which we had before. And so the formula for sample size is that you can find the sample size by taking the z of the alpha over 2 plus the z of beta, squaring those, multiplying them by the variance, or sigma squared, and dividing by the difference of the means squared. And so what we have when we actually fill in those numbers is we have 2.58 plus 0.84 squared times 60 squared times 30 squared. And so that is equal to 11.969 times 3,600 divided by 900. And that gets us 46.79, which I need to round up to 47. So I just want to make the point here really quick that when your sample size was only equal to 12, your power of this test was equal to 0.1977. If you want the power to be equal to 0.800, we needed an N of 47. This is why we always talk about, if you want to increase the power of your test, increase the sample size. If you want your results to be more consistent, increase your sample size. That is the best thing you can do to have your test actually perform the way you want it to, is to increase your sample size. So the last problem that we're going to do is problem 4. And this problem is a t-test. And our t-test is remarkably similar to the z, except we're using our t-test statistic, because our t-distribution can be used when we have an unknown variance of the population and a small sample size. And we use the t-test a lot because that's often what we have. So we're looking at a hypothesized mean of 12 versus a hypothesized mean that is not 12. So our H naught and our alternative hypothesis, this immediately tells us it's a two-sided test. Our N is equal to 12. The sample mean, X bar, is equal to 12.564. And our standard error on the mean was given as 0.296. And so this was given as a little like computer output thing, and you were told you're going to need to find a couple of values. And so this is just practicing manipulating the formulas and using the t-test statistic to see how we do hypothesized testing. So the first thing it asks for is degrees of freedom. And degrees of freedom is equal to n minus 1. So in this case, it's equal to 12 minus 1, or 11. The next thing it asks is to find the missing values. And so our missing values are our sample standard deviation, our test statistic, and our p-value. Those are the things that we don't have from the output. And so we'll start with the sample standard deviation. And that is equal to the standard error multiplied by the square root of n. And so we have both of those things. So we know the standard error is 0.296, and we multiply that by the square root of 12, and we get 1.025. Now that we have our standard deviation, we can go ahead and calculate our test statistic, and that is equal to x bar minus mu over the sample standard deviation divided by the square root of n. And so we have 12.564 minus 12 divided by 1.025 divided by the square root of 12. And so that crunches down to 1.905 as our test statistic. And the question asks us if it's possible to reject the null hypothesis at the 0.05 level of significance. And so to do this, what we're going to do is we're going to look at the t values for a 0.05. So can we reject at 0.05? So our t of alpha over 2 comma n minus 1, if we're looking at 0.05, that's 0.05 divided by 2 and 12 minus 1. So that means we're looking at t of 0.025 with 11 degrees of freedom. And that value is 2.201. And we know from our basic hypothesized testing that if t0 is less than the test statistic for that t of alpha over 2 and minus 1, that we are going to fail to reject it. So because 1.905 is in fact less than 2.201, we accept or fail to reject the null hypothesis equal to 12 at the 0.05 significance level. So the next question, they get kind of out of order in my opinion here, but they ask you if it's a one-sided or two-sided test. We kind of needed to know that before we got started, but it's a two-sided test. I would have had that be the first question. And so we already knew that because it was mu versus mu does not equal. And so we know that it's a two-sided test. So then it asks us to construct the 95% confidence interval on the mean. And so we already looked at what t of 0.05 over 2 comma 11 is equal to. We said that was equal to 2.201. And so we're just going to set up our confidence interval that x bar minus t alpha over 2 n minus 1 times the sample standard deviation divided by the square root of n is less than or equal to mu is less than or equal to x bar plus t alpha over 2 n minus 1 times s over the square root of n. And so in this case, that equals 12.564 minus 2.201 multiplied by 1.025 divided by the square root of 12. It's less than or equal to mu is less than or equal to 12.564 plus 2.201 times 1.205 divided by the square root of 12. And so we have a lower limit as 11.913 and an upper limit of 3.215 as our confidence interval. And so that was the exam review. Again, if you have any questions at all, please do not hesitate to ask. And everybody take care, be healthy, and be happy.